Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today because we're going to uncover some of the most massive, hidden forces that are continuously sculpting the very ground beneath our feet. You know, we often walk outside, see a hill, a valley, or even a mountain, and kind of just think of them as permanent, unchanging fixtures. But the truth? The truth is far more dynamic and honestly, incredibly fascinating. Our planet is constantly acting as a master architect, building and rebuilding its surface in real time.
So it really begs the question, have you ever wondered what colossal forces built the highest peaks in the deepest ocean valleys? It's super easy to look at a mountain range and just see static rock, but what we're actually looking at is a snapshot of an active, ongoing construction site. Today, we're going to look straight at the architect's blueprint. We're going to break down exactly how the Earth folds, snaps, and erupts to create the world as we know it.
Okay, let's dive into this with Section 1, Mountains Through Deep Time.
To really understand mountains, we kind of have to completely rewire how we think about time. We have to think in geological time, where 1,000,000 years is, quite literally, just a blink of an eye. You see, the age of a mountain range fundamentally defines its structure, its height, and its very foundation. Looking at the Earth's timeline here, the Precambrian mountains, like the Laurentian, date back a staggering 4.6 billion years to the Earth's very origins. Fast forward to the Caledonian period 320 million years ago, creating the Aravallis, and then the Hercynian period 240 million years ago, which gave us the Urals. But check out the Alpine Fold Mountains, which include the towering Himalayas. They are just 30 million years old. In Earth's history, they are practically brand new additions. Actually, that's exactly why they're still some of the youngest and highest mountains we have today.
All right, let's move on to Section 2, the power of folding, focusing on crustal compression.
So how do these massive structures actually rise up out of the ground? To get this, we need to shift our focus to the mechanical forces at play on the mainland. Specifically, it's all about compression. That's this incredible squeezing force acting on the Earth's crust. Imagine laying a rug flat on the floor and just pushing the two ends together. The rug has nowhere to go but up and down in waves, right? Well, when sedimentary rocks that were deposited in shallow seas get squeezed, they form these exact same massive waves. The upward bending wave is called an anticline, and that downward bending trough is the syncline. This incredible, relentless pushing force is what creates the highest arc-shaped mountains in the world.
But you know, the crust doesn't just fold in one simple, perfect wave. Continued pressure warps the rock into incredibly complex structures. You start with a simple fold, but as the squeezing continues, it gets uneven, creating an asymmetrical fold. Keep pushing and it becomes an overfold, literally pushed over onto itself. Extreme pressure can create a recumbent fold, where the rock is lying almost completely flat, or even a nap, where the fold actually shears and is thrust completely over a fault line. What's absolutely fascinating is that these massive folds generally align in specific directions. For instance, north-south for the Rockies and Andes, or west-east for the Himalayas and the Alps.
Now, let's look at the flip side in Section 3, Breaking the Crust, where we talk about faults and tensions.
Because as it turns out, the crust doesn't just bend. When the forces pulling the crust apart, which we've called tension, outpace the forces squeezing it together, the crust literally snaps. Now, what's really interesting here is the contrast. On one hand, fold mountains are driven by compression, which shortens and thickens the crust. But on the other side, block mountains are driven mostly by tension. Instead of squeezing rock together, tectonic forces are pulling it apart. And because rock can't exactly stretch like a rubber band, it fractures, it faults, and massive blocks of it actually subside or sink straight downwards.
To see exactly how this works, think of taking a freshly baked cake and slicing it into 3 sections. First, tensional forces pull the cake apart slightly. Second, fault lines, or, the cracks from your knife, develop. Third, as you pull those outer pieces away, that central block of cake just drops down. On Earth, that dropped center section forms what we call a rift valley. The perfect real-world example of this is the massive East African Rift Valley. And those outer blocks that are left towering on the sides, those are called horsts.
So, to be totally clear, a horst is an upstanding block of crust left towering between subsided fault blocks. You might also hear it called a block mountain. Great examples of these are the Black Forest Mountains in Germany or the Vindhyas in India. So if you ever see a mountain that looks more like a sudden, sheer block of rock rather than a rolling wave, you're more than likely looking at a horst created by tension and faulting.
All right, so we've explored how the mainland buckles and breaks, but what happens when these massive tectonic forces act out at sea? Let's leave the continental mainland behind for a minute and plunge straight into the ocean's depths.
Welcome to Section 4, Architectures of the Sea, looking at island formations.
And this brilliantly illustrates a key concept. When land merges from the ocean waters, it generally falls into two primary categories, based entirely on how it was architected by the Earth. There's a fundamental difference in how they're built. Continental islands are essentially just extensions of the mainland that happen to be flooded by shallow water. They're connected by straits, channels, or shallow lagoons. Oceanic islands, on the other hand, have absolutely zero connection to the continental shelf. They rise entirely independently from the deep, dark ocean floor.
These islands are just incredibly diverse. Under continental, you've got your individual islands like Madagascar or Newfoundland. You have massive archipelagos like the British Isles. And you have island arcs or festoons, which form loops around the mainland when one tectonic plate subducts under another. Think of the Andaman and Nicobar Islands. Meanwhile, oceanic islands rely on entirely different forces. They're either the towering tops of mostly extinct volcanic cones pushing up from the seafloor, like Mauna Loa or the Galapagos, or they're biological marvels built by tiny coral formations, like the Maldives and Bermuda.
Let's move to our final topic and see how this all builds up in Section 5, Earth's hidden thermal engines.
To understand how some of the most famous oceanic islands in the world are actually formed, we have to travel deep underground to a very specific localized power source, a hotspot. A hotspot is a supremely hot region deep within the Earth's mantle. It's a massive thermal anomaly that acts kind of like a blowtorch, punching right through the crust from deep inside the planet. This intense heat is responsible for incredible volcanic activity and can even heat underground water straight to the boiling point, creating those amazing surface geysers.
What's really mind-blowing is how rare they are. There are only about 40 to 50 of these localized hotspots scattered across the entire globe. Just 40 to 50. But despite their tiny numbers, their impact is absolutely monumental. Some of the most famous volcanic and geographical anomalies out there, like the erupting fissures in Iceland or the unique ecosystems of the Galapagos Islands, are driven directly by the heat of these localized engines.
So, the crucial point here, and honestly this is perhaps the most fascinating takeaway of this entire explainer, is what hotspots reveal about our planet. You see, the hotspot itself remains largely stationary deep in the mantle, but the Earth's tectonic plates above it, they're constantly moving. So the hotspot acts like a stationary tracking beacon. As the oceanic crust slowly drifts over the blowtorch, the hotspot creates a volcano. Then the plate moves, and it creates another one, and another one. This process leaves a trail of islands, creating entire chains like Hawaii. Looking at a hotspot island chain is quite literally looking at a physical map of how our massive tectonic plates have drifted for over millions of years. It's like a giant geological breadcrumb trail.
Which leaves us with this final thrilling thought. If the crust is constantly folding under compression, faulting under tension, and drifting over stationary hotspots, the Earth's map is never truly finished. If hotspots track the continuous drift of our tectonic plates today, what new mountains and islands will Earth's hidden engines build next? It is absolutely incredible to think that the geography of the future is being sculpted beneath our feet right this very second. Thank you so much for joining me on this explainer. I really hope you now have a deeper appreciation for the majestic blueprint of our planet. Until next time, keep looking closely at the world around you.